Hi, I'm Jason Collins, and this video is about how people care about resource distribution. In 2008, when the Sacramento Bee created a database of California state worker salaries, University of California employees could learn about their colleagues' pay for the first time. Researchers at 3 UC campuses studied the impact by randomly emailing some employees about the database. Employees who learned they earned below the median for their department and role reported lower job satisfaction and began searching for new positions. The effect was strongest among workers in the bottom quartile of their unit's pay scale. A follow-up 2 or 3 years later suggested more lower paid employees had left their positions. In contrast, employees above the median showed no changes in satisfaction or behaviour after learning about peer salaries. This research shows that people care about their relative position to others, not just their absolute circumstances. The dissatisfaction and subsequent job seeking of low-paid UC employees revealed distributional preferences, preferences about the allocation of resources across individuals. To understand how social comparisons influence economic decisions, we can model these distributional preferences mathematically. Economists model distributional preferences by extending utility functions to include others' outcomes, just as we model preferences over personal consumption. This approach allows us to analyse how social considerations influence economic decision-making in contexts ranging from charitable giving to workplace compensation. Understanding distributional preferences can help us explain behaviour that deviates from pure self-interest in experimental games. We can use them to examine how inequality and social comparisons affect economic decisions. This can inform the design of workplace arrangements and economic policies that account for social preferences. In what follows, I examine 2 forms of distributional preferences in detail: altruism and inequality aversion, and consider other social preferences. Each helps explain different aspects of observed behaviour, from charitable giving motivated by altruism to rejection of unfair offers driven by inequality aversion. Altruism. Altruism is concern for the outcomes of others, with positive weights on others' well-being. To incorporate altruism, we give a positive weight to the utility of others in the utility function. Here's a simple example, where an individual's utility depends on both their own outcome and another person's. The utility of agent I, U sub I, is a function of the outcome for agent I, X sub I, and agent J, X sub J. Alpha is some number greater than 0, with utility increasing linearly with an increased payoff for either agent. Altruism comes in 2 forms. Pure altruism reflects genuine concern for others' well-being. Impure altruism occurs when people get a warm glow from doing good, regardless of the actual impact on others. Example: the public goods game. Consider a public goods game where 2 players each have $10 and must simultaneously decide how much to contribute to a public project. The total contributions are multiplied by 1.5 and split equally between both players, regardless of their individual contributions. This game captures real-world situations: work teams deciding effort on shared projects, neighbours contributing to community improvements, or countries investing in climate change mitigation. For this scenario, if both players contribute their full $10, the pot becomes $30 and each receives $15. If neither contributes, each keeps their $10. If one contributes $10 and the other nothing, the $15 pot is split equally, so the contributor finishes with $7.50 and the non-contributor ends up with $17.50. A self-interested player would contribute nothing. For any contribution by the other player, keeping your money always gives a higher payoff. However, both players would be better off if they both contributed everything. Now suppose both players have altruistic preferences, placing a positive weight on the other's outcome, albeit lower than the weight on their own outcome. With these preferences, we can calculate whether contributing is optimal if the other person contributes. If the agent contributes, they receive utility from their $15 and the $15 received by the other agent. Utility of contributing equals 26.25. If they do not contribute, they receive utility from their higher payoff of $17.50, but the lower payoff of $7.50 for the other agent acts as a drag. The utility of free riding equals 23.125. With these altruistic preferences, contributing is optimal when the other player contributes. The weight placed on the other player's payoff, alpha equals 0.75, makes cooperation the best response to cooperation. Contributing is actually the best response to any contribution by the other player. For example, here are the payoffs in response to a contribution of $0 by the other player. If the agent contributes, they receive utility from their $7.50 and the other player's $17.50. The utility of contributing is 20.625. If they do not contribute, they receive utility from their higher payoff of $10, but the lower payoff of $10 for the other player reduces their utility more than they gain for the increased personal payoff. The utility of free riding is 17.5. An altruistic player will contribute even if the other player is not an altruist. This example shows how moderate altruism can overcome the free rider problem in public goods provision. The positive weight two altruistic players place on the other's outcome makes mutual contribution a Nash equilibrium. Limitations of the altruism model. While altruism helps explain behaviours like charitable giving, it has its limitations. Recall the ultimatum game. The first player, the proposer, receives a sum of money, say $10, and must offer some portion of it to the second player, the responder. The responder then has two options. Accept the offer, both players get the proposed split. Reject the offer, both players get nothing. Altruism can explain why proposers make generous offers, but it fails to explain why responders often reject low offers, knowingly reducing both players' payoffs. Such rejection would require negative weights on outcomes, contradicting the altruism model. Inequality aversion. Inequality aversion offers an explanation for such rejections. We dislike being worse off than others, and to a lesser extent, we may feel uncomfortable being better off than others. This captures the intuition that people care about relative standing. Think of how employees react to learning their co-workers earn more, or the guilt some feel about their wealth relative to those in poverty. To understand how inequality aversion affects decision-making, we need a formal way to represent these preferences. Fair and Schmidt, 1999, developed an influential model that captures both the dislike of having less than others and the potential discomfort of having more. In their model, the utility of agent I, U sub I, is a function of the payoff of agent I and the payoff of agent J. Each term in this equation represents a distinct psychological effect. X sub I is their own outcome, such as their payoff or salary. Alpha max, X sub J minus X sub I, 0, captures the sting of disadvantageous inequality, like discovering your colleague earns more than you. Beta max X sub I minus X sub J, 0, represents the discomfort of advantageous inequality, like feeling guilty about your high salary compared to others, or the guilt of making a low offer in the ultimatum game. The max function ensures that only the relevant term is included. If agent I has more than the other player, with X sub I higher than X sub J, the disadvantageous inequality term is 0. If agent I has less, the advantageous inequality term is 0. To present the utility function in a form you may find more intuitive without the max function, we can rewrite it with utility of agent I being their own payoff minus a penalty for either advantageous or disadvantageous inequality. Typically, alpha is greater than beta, as people dislike having less than others more than they dislike having more than others. We can also set beta less than 0 for an agent that likes to be better off than others. To visualize how inequality aversion affects utility, the following graph shows a plot of utility as a function of x sub I. This utility function has a kink at x sub j, where agent I moves from having less to more than agent j. Below x sub j, utility increases due to both the increasing material outcome for agent I plus the reduction in inequality. If beta is between 0 and 1, as in this diagram, the utility of agent I, u of x sub I, continues to increase in x sub I above x sub j, but at a decreasing rate, as inequality degrades the benefits of having more. Example: the ultimatum game. This theoretical model of inequality aversion helps explain real-world behaviours that cannot be explained by pure self-interest. This includes behaviour in the ultimatum game, a classic example where people often act against their material self-interest. A purely self-interested responder should accept any non-zero offer, as something is better than nothing. Yet people often reject unfair offers, such as job candidates rejecting a low salary even though this leaves both parties worse off. The pain of inequality outweighs the cash. Suppose the responder in the ultimatum game has inequality-averse preferences with beta equals 0.25 and alpha equals 0.5. What offers X would the responder reject where the proposer has $10 to split between them? If the responder rejects, the payoff to the proposer and the responder is 0. That is, X sub P equals X sub R equals 0. If the responder accepts, the responder receives X and the proposer keeps the remainder. That is, X sub P equals 10 minus X and X sub R equals X. The responder will accept if the utility of accepting is greater than the utility of rejecting. I will examine offers above and then below $5. First, I will look at offers above. We substitute the utility function into the inequality. As the alpha term equals 0, I do not include it here. We then enter the ultimatum game outcomes for acceptance and simplify. This inequality will hold for any beta less than 1, as x is greater than or equal to 2x minus 10 for any x less than or equal to 10. Therefore, the condition will hold for the agent with beta equals 0.25. Recall that if beta is less than 1, the responder has higher utility from a higher payoff, but at a decreasing rate when they have more than the proposer. When the offer is below $5, the responder gets less than the proposer, so only alpha matters. Again, I substitute the utility function into the inequality, enter the ultimatum game outcomes, and simplify. The responder with alpha equals 1/2 will reject offers below $2.50. We can plot the utility of the responder as a function of the offer X. As the offer is not independent of the proposer's payoff, I will derive the shape of the utility curve as a function of XR equals X. I do this by substituting the payoffs and values of alpha and beta into the utility function. We can also rearrange this equation to explicitly show the slope of the curve. I first manipulate the equation into a form showing the slope times x plus intercept. I then simplify. The utility of the responder with respect to x equals 2x minus 5 if x is less than 5, or 0.5x plus 2.5 if x is greater than or equal to 5. This diagram shows the responder's utility curve as a function of the offer x. The slope of the curve for x is less than 5 is 1 plus 2 alpha equals 2, and for x greater than or equal to 5 is 1 minus 2 beta equals 0.5. These slopes differ from our earlier inequality aversion utility plot because here, any gain for the responder means an equal loss for the proposer. This relationship creates a double effect on inequality. Consider an offer increase from $4 to $5. The responder's payoff rises by $1, but the gap between players shrinks by $2. This explains why the slope is steeper when behind. The opposite happens when the responder is ahead. If the offer increases from $6 to $7, the responder gains $1, but inequality grows by $2. This larger penalty for inequality acts as a drag on utility, making the slope flatter. The curve has a kink at x equals 5, where the responder moves from having less to more than the proposer. The point where the curve crosses the x-axis represents the point below which the responder would reject the offer. Example: the dictator game. While the ultimatum game shows how inequality aversion affects responses to unfair offers, the dictator game helps us understand how inequality aversion might influence giving behaviour. In the dictator game, the dictator makes a unilateral offer to the receiver. The game then ends. The receiver has an empty strategy set. In this version of the game, the dictator has a constrained choice set and must decide between the allocations 0, 1 and 1, 5. That is, the dictator must choose between 0 for themselves and 1 for the receiver, or 1 for themselves and 5 for the receiver. The dictator's alpha equals 1/2. As the dictator has less than the other player under each distribution, alpha is the relevant parameter. We calculate the dictator's utility of each allocation. The 0, 1 allocation gives a utility of 0 for the dictator's payoff minus alpha times the inequality. The utility of 0, 1 for the dictator is minus 1/2. The 1, 5 allocation gives a utility of 1 for the dictator's payoff minus alpha times the larger inequality. The utility for the dictator of 1, 5 equals minus 1. The dictator prefers to allocate 0, 1 as the cost of the inequality is greater than the benefit from the increased payoff. Alpha greater than 0 can also account for the rejection of low offers in the ultimatum game. Other distributional preferences. While altruism and inequality aversion explain many observed behaviours, they are not the only types of social preference. Rearranging the inequality aversion model reveals the direct weights people place on others' outcomes. Where x sub I is greater than x sub j, agent I places weight of beta on the other's outcome and 1 minus beta on their own. Where x sub I is less than x sub j, agent I places the weight of minus alpha on the other's outcome and 1 plus alpha on their own. Arranging this way makes the weight given to the outcomes for each agent more transparent. It provides a more intuitive way to consider some distributional preferences. Charnas and Rabin 2002 used this form with parameters sigma and rho, where sigma equals minus alpha and rho equals beta. We'll follow their approach, since having parameters with the same sign makes the analysis more intuitive. Forms of distributional preferences. We can adjust the values of rho and sigma to capture many forms of distributional preferences. Some are as follows. An altruistic agent has sigma greater than 0 and rho greater than 0. They weight others' payoffs positively in all situations. When someone else gains $1, it directly increases the agent's utility, regardless of whether they are ahead or behind. Compared to our earlier altruism model, this model allows for different degrees of altruism depending on the relative payoffs of the two agents. An inequality-averse agent has 1 is greater than or equal to rho, which is greater than 0, which is greater than sigma. They like gains for others who are behind, but dislike falling further behind themselves. This inequality is equivalent to alpha greater than 0 and beta greater than 0 in the Fair-Schmidt model. A status-seeking agent has 0 is greater than rho is greater than or equal to sigma. Not only do they dislike others gaining, they actively prefer having more than others. Their utility goes up when either they get more or the other player gets less. A classically self-interested agent has rho equals sigma equals 0. Their utility depends only on their own payoff. A Rawlsian agent has rho equals 1 and sigma equals 0, making their utility u sub I of x sub I x sub j equals min of x sub I x sub j. They maximize the minimum payoff across all players, showing pure concern for the worst off individual. A utilitarian agent has rho equals sigma equals 1/2, making their utility u sub I of x sub I x sub j equals x sub I plus x sub j. They weight everyone's payoff equally and simply sum the total, caring about efficiency rather than distribution. Example, the trust game. Let's use this form of the utility function to analyse the outcomes in a trust game, where an investor must decide whether to trust an entrepreneur with their money. The trust game provides a lens for understanding how social preferences affect economic transactions, where success requires sequential cooperation and trust. The trust game captures two real-world dynamics. First, one must choose whether to make themselves vulnerable to exploitation by trusting the other. Second, the trusted party must then decide whether to honour or betray that trust. This structure mirrors some common economic situations. Investors must decide whether to trust entrepreneurs with capital before knowing if they will act in good faith. Business partners often need to commit resources before knowing if their counterparts will uphold their end of the deal. Even simple transactions, like paying in advance for services, involve one party trusting another to deliver as promised. In an earlier video, I considered a scenario between Linda, a potential investor, and Marco, an entrepreneur. This mirrors common situations where investors must decide whether to trust entrepreneurs with capital, and entrepreneurs must choose between short-term gain and maintaining their reputation. The choices will depend not just on monetary payoffs, but on how each values the other's outcomes. Linda is looking for investment opportunities. She identifies a promising crypto-based startup created by Marco. Marco is looking for seed funding. Linda can invest $10. If Linda invests, her investment will triple in value. Marco can then decide to either shut down the startup and keep the $30, or maintain the startup in the market and pay a $15 dividend to each of Linda and himself. If Linda does not invest, Linda keeps the $10. The startup gets 0. Marco is effectively playing a dictator game. If he were purely self-interested, he would shut down and keep the $30. As a result, a purely self-interested Linda would not invest. Let's examine both players' actions if their utility functions place weight on the outcome of the other. U sub L and U sub M are Linda and Marco's utility. X sub L and X sub M are the outcomes for Linda and Marco. Linda's utility function shows moderate concern for Marco's outcomes. When Linda is ahead, she places more weight on Marco's payoff, rho equals 2/3, than her own, 1 minus rho equals 1/3, suggesting significant altruism. When she's behind, she still values Marco's payoff positively, sigma equals 1/3, but prioritizes her own outcome, 1 minus sigma equals 2/3. Marco's preferences are more asymmetric. He shows concern for Linda's outcomes only when he's ahead, otherwise focusing solely on his own payoff. This asymmetry reflects a mix of self-interest and conditional altruism. If Marco and Linda know each other's utility functions, what is the equilibrium with these distributional preferences? If Linda chooses trust, Marco has a choice between $15 each and $30 for himself. Marco calculates the utility of each option. The utility for Marco of 1515 equals 15. The utility for Marco of 0.30 is 7.5. Marco receives high utility by paying the dividend to Linda. We can also calculate Linda's utility for each of Marco's options if she chooses to trust. The utility for Linda of 1515 equals 15. The utility for Linda of 0.30 is 10. Linda's utility is higher if Marco pays a dividend. For the other node, if Linda does not invest, she will keep $10. Marco will have nothing. Each has the following utility from that failure to invest. The utility for Marco of 10.0 is 0. The utility for Linda of the distribution 0.10 equals 3.33. Putting these payoffs into the extensive form of the game, we get the following, with payoffs of 15.15 if Linda invests and Marco returns a dividend, 10.7.5 if Linda invests and Marco does not return the dividend, and 3.330 if Linda does not invest. To solve for the game's equilibrium, we use backward induction, starting with Marco's decision if Linda invests. Marco can return a dividend for utility 15 or shut down for utility 7.5. He chooses to return the dividend. As a result, Linda will invest for utility 15 rather than not invest for utility 3.33. Linda invests.